I want you to try a visualization exercise with me. Just close your eyes for a second.
Okay.
Imagine you're sitting in the left seat of an Airbus A320. You're the captain. And it is not a sunny day in the Maldives.
I'm guessing it's pretty terrible outside.
Oh, it's pea soup fog.
Okay.
We're talking London or Frankfurt on a really bad morning, what pilots call Category 3 conditions.
Right, which means visibility is effectively zero. I mean, you can't see the nose of the plane, let alone the runway lights. You're just hurtling through this gray void at, what, about 140 knots?
Exactly. And because you can't see, you're relying entirely on the automation. The robot is flying the plane. Your hands are hovering right near the controls, but you aren't touching them.
You're just monitoring.
Right. You're just watching the dashboard.
Yeah.
So you pass 200 feet, then 150. You are literally seconds away from hitting the ground. And then right at 90 feet.
Less than 10 seconds from impact.
Yeah, right at 90 feet, Pop.
Oh, man, the nightmare scenario. The flight control unit, the FCU, just goes dark.
The lights just go out. The digital green numbers for your speed, heading, altitude, they just vanish. The actual knobs you use to tell the plane what to do are dead.
Yeah.
It's just a black strip of plastic now.
Yeah.
So be honest with me here. What is your lizard brain screaming at you to do in that split second?
Oh, panic. Absolute panic.
It has to be, right?
It's the startle response. It's a pure physiological survival mechanism. You get this massive dump of adrenaline because your brain is just screaming, I'm blind, I've lost control, save the ship.
Right.
And your instinct in that moment is to just grab the side stick, slam the thrust levers forward, and get the heck out of there. You want to go around, abort the whole thing.
Which makes total sense because usually in any other machine we operate, if the interface breaks, the whole system is broken. Like if I'm driving down the highway and my car dashboard goes completely black and the steering wheel feels weird, I'm pulling over, I'm stopping.
Exactly. It's totally counterintuitive to keep going. But today we're doing a deep dive into a really fascinating source document titled The Captain's Lens, Auto-Land Logic Beyond Alert Height.
Yeah.
And the central argument this document makes is, well, it's going to sound completely insane to anyone who likes having control.
Which is what?
That in this specific moment, 90 feet off the ground, blind, with a dead dashboard, the absolute safest thing you can do
Is what?
is sit on your hands and do absolutely nothing.
What? Not a single thing.
Okay, see, that is a really bold claim. Telling a pilot to do nothing when their controls literally die just sounds like a great way to become a crater.
It does.
So today, our mission for this deep dive is to get inside the brain of the Airbus A320. We need to figure out why the engineers designed it this way, and why your human survival instinct is actually the thing most likely to kill you in this scenario.
Yeah, it's really a story about psychology, physics, and this very specific invisible line in the sky. Let's start with the basics of the failure before we get into the psychology of it all. We mentioned the FCU. For our listeners who maybe aren't A320 pilots or system engineers, what exactly are we looking at when we say FCU?
So the flight control unit is that horizontal panel right under the windshield glare shield. It's the primary interface.
Okay.
Think of it like the keyboard and monitor for your desktop computer. It's where you input what you want. Like, I want speed 250, I want heading 090, and it's where you actually see what the plane is doing.
So it's the user interface. It's the mouse and the screen.
Exactly, it's the UI. And in our visualization we just did, the UI just crashed. Black screen, total unresponsiveness.
Right. Now, the document talks heavily about this invisible line called alert height. And this seems to be the pivot point for everything we're talking about today. What is alert height?
Alert height, or AH, is this critical system boundary. For an Airbus doing a Category 3 auto land, that zero visibility landing we talked about, this line is usually drawn at 100 feet above the runway.
100 feet. I mean, that is very low.
Extremely low. You're talking about maybe 6 or 7 seconds from the main wheels touching the concrete. And the whole engineering philosophy changes completely depending on which side of that line you're on.
Like a switch flips.
It's exactly like crossing a border. The laws of physics and the laws of system logic just change.
Okay, so let's test this border. Say I'm at 200 feet. So I'm above alert height, and my FCU fails. Both channels just die. What happens then?
Okay, so if you are above 100 feet, the system treats a dual FCU failure as a critical event. The logic basically says, hey, we've lost the interface, we can't guarantee the pilot knows what's happening, and we still have enough altitude to recover safely.
So it yells at you.
Oh, yeah. You'll get a warning chime. The red Autoland light might start flashing right in your face.
And the procedure for the pilot.
You get out of there, you execute a go-around, you apply full power, you pull the nose up, and you fly away to troubleshoot the problem at a safe altitude.
Because you have time. You have the altitude to transition safely from descending to climbing.
Correct. And this is the but once you cross that invisible barrier of 100 feet, once you are below alert height, the logic flips 180 degrees.
Yeah, and the source material had this line that really stuck out to me. I actually had to read it twice. It said that below 100 feet, a dual FCU failure is, quote, no longer considered critical.
Which is just a wild sentence to read in an aviation context, isn't it? No longer critical.
It's completely baffling. I'm 90 feet from the concrete. I literally can't see out the window. My entire control panel is dead. And the Airbus manual basically shrugs and says, it's fine.
Yeah.
Why? Why does the danger rating somehow drop when the danger seems like it's at its absolute highest?
This is where we have to talk about physics. Specifically, we're talking about inertia and energy states. At 90 feet, the aircraft is considered committed.
Committed to the crash or committed to the land.
Committed to the ground.
Yeah.
Think about the massive energy involved here. You are a 70-ton metal tube descending at a very specific angle toward the runway. Your engines are at idle or very near idle. You're heavy and you are very low.
Okay, I picture that.
So to interrupt that momentum, to spool up those massive jet engines from idle all the way to full go-around power, which takes a few seconds, and to pitch the nose violently up, to reconfigure the flaps, that is a massive, violent change in energy.
And you're trying to manage that violent change in zero visibility.
Exactly. This is the absolute key to the whole thing. If you try to go around at 50 or 60 feet in dense fog, the risk of spatial disorientation is huge.
Your body plays tricks on you.
Right. Your inner ear can completely trick you. Without visual references, the acceleration feels like you're pitching up too much, so you push the nose down.
And you hit the runway nose first.
Or you pitch up too steep and stall 50 feet in the air.
So the engineers basically calculated the risk of both options.
They did. They sat down and asked, what is statistically more dangerous? Letting the computer finish the landing sequence with a broken screen? Or asking a startled, adrenaline-pumped human being to suddenly hand-fly a missed approach in the pitch dark?
And the math just flat out says the human is the massive risk factor.
The human is the weak link. Trying to abort below 100 feet introduces pure chaos. Continuing the auto land is stable.
Okay, I want to dig into that stability, though, because this is the part I really struggled with in the source. If the FCU is dead, isn't the autopilot dead? I mean, going back to your computer analogy, if I unplug my keyboard, I can't type. If the FCU is the interface, how is the plane still flying?
This is the knobs versus brains distinction, and it's probably the most important thing to understand about modern avionics architecture.
Knobs versus brains. Okay, break that down for us.
The FCU, the knobs on the dashboard, are just the request mechanism. They are the mouse. But the actual brain of the operation is the FMGC, the flight management and guidance computer.
Okay.
That's the heavy tower sitting under the desk doing all the actual processing.
The actual CPU.
Right. Now, the source explains that below 100 feet, the A320 logic locks into a very specific mode called land mode.
Land mode. That sounds pretty definitive.
It is very definitive. Think of it like a roller coaster locking onto the track. Before land mode engages, you could steer left, you could steer right, change your altitude. But once land mode engages and you cross that 100-foot threshold, a logic lock occurs.
A logic lock?
Yeah. The system essentially freezes the configuration.
So it stops listening to the knobs entirely.
It completely stops caring about them. The command authority transitions away from the FCU channel and goes directly to the FMGCs.
So wait, even if I started spinning the heading knob frantically at 90 feet, trying to tell the plane to turn...
The plane would completely ignore you. It doesn't matter that the lights are out on the panel because the plane isn't even looking at the panel anymore. It's executing a highly choreographed script that is hard-coded into its memory.
That's honestly a bit unnerving, isn't it? The plane just deciding, hey, I'm not listening to you anymore, I'm landing.
It's unnerving if you want control. But it's incredibly comforting if you want to survive the next 10 seconds. You have to remember, the FMGCs are highly redundant. There isn't just one computer. There are two, sometimes more, constantly cross-checking each other.
Okay.
And crucially, they do not need the FCU to function. The brain is perfectly healthy. It's only the face that's paralyzed.
But wait, a brain needs senses, right? If the dashboard is dark, where is the plane getting its physical information? It's flying blind too, isn't it? If the screen is dead, how does it physically know where the runway is?
Not at all. The pilot is blind. The plane has 20/20 vision.
How? What is it looking at?
The source goes into great detail about the independent data streams. The FMGC has direct lines to the aircraft's sensors that bypass the broken FCU completely. First up, it has the ILS.
The instrument landing system.
Right, that's a precision radio beam shooting up from the runway itself. It tells the plane, hey, you're a little left of center line, you're a little low on the glide slope. The FMGC is reading that raw radio signal directly. It doesn't need to display it on the FCU to know what to do with it.
Okay, so it knows where the runway is laterally. But what about height? That seems pretty crucial for not slamming into the ground.
That's where the radio altimeters come in. These are radar transceivers located on the belly of the plane. They basically bounce a signal straight down to the ground and time the return.
Oh, wow.
They know the exact height of the aircraft down to the single foot.
So that's its depth perception.
Precisely. It's flawless depth perception. And then you have the ADRs, the Air Data Inertial Reference System.
ADR's airs, that sounds like the plane's inner ear.
That is exactly what it is. It senses acceleration, attitude, pitch, roll. It knows perfectly if the plane is level or banked. So imagine this exact scenario. The pilot is sitting there looking at a dead black piece of plastic.
Yeah.
Sweating, but the FMGC is sitting down below with radio eyes locked onto the runway, radar depth perception tracking the ground, and a perfect inner ear for balance.
So it doesn't need the dashboard lights to know it's 50 feet off the ground?
No, not at all. The guidance computer takes all that raw sensor data and sends commands directly to the servos, the physical muscles that move the ailerons and the elevators. It cuts out the middleman entirely.
Okay, so let's walk through the actual physical sequence here. I want to feel what this is like in the cockpit. I'm the pilot. My screen is dark. I'm sitting on my hands, fighting every single urge to grab the stick. What is the plane physically doing around me?
It's executing a precision mechanical dance. At 100 feet, it's strictly holding the runway center line using that localizer signal. Then at about 40 to 30 feet, it automatically initiates the flare.
The flare. That's the critical moment where you pull the nose up to soften the actual impact.
Right. Yes. And timing that maneuver by hand in zero visibility is incredibly dangerous and hard. Usually a pilot relies on peripheral vision, seeing the ground rush up in their periphery, but you obviously don't have that in thick fog.
Right.
But the computer uses that radar altimeter data we talked about to time the pull-up perfectly. And it simultaneously cuts the engine thrust to idle at the exact right millisecond.
So as a pilot, just sitting there in the dark, you'd actually feel the nose pitch up around you.
Yes, you'd feel the G-force shift during the flare. You'd hear the massive engines spool down to idle, and then thump. The main gear touches down on the concrete.
And what about after the wheels hit? You're still moving incredibly fast down the runway.
It instantly transitions into rollout mode. This is where the autopilot uses the rudder pedals to keep the plane glued to the absolute center line of the runway, while simultaneously applying the auto brakes and the reverse thrust.
And all of the flare, the rollout, the braking, all of this happens with a completely dead FCU.
A totally dead FCU. The autopilots mechanically track the center line and manage the thrust entirely independently. The plane lands itself, flares itself, and steers itself to a safe speed.
It's really incredible when you think about it. We often talk about automation dependency as this bad thing in aviation. Like, oh, pilots these days can't really fly, they just manage computers.
You hear that a lot.
Right. But in this specific slice of time, below 100 feet in the fog, automation dependency isn't a weakness, it's the safety net.
It is the ultimate safety net, but, and here is the huge catch, the engineering only works if the human being doesn't mess it up.
The human factor. Because humans are famously bad at doing nothing when they are terrified.
Exactly. The source mentions a core Airbus philosophy. No single point of failure should ever compromise flight safety. The entire system is beautifully designed to trap errors and survive hardware failures, but the one thing the system cannot control
Is you, the pilot.
Is you. The startle response we talked about at the very beginning. If you, the pilot, give in to that fear, if you grab the stick and yank it back because the screen just went dark, you are overwriting the survival logic.
You're disconnecting the brain that actually knows what it's doing.
You are taking a perfectly stable aircraft, which is literally milliseconds away from a safe touchdown,
Right.
and you are turning it into a chaotic projectile. You are blinding the system that actually sees.
Wow. So the actual do in this emergency procedure is just monitor.
Monitor. And I know it sounds passive, but it's actually an active discipline. You sit there, you watch your standby instruments, the backup artificial horizon, you keep your hands near the controls but strictly not on them, you feel what the plane is doing, you wait for the landing gear to make contact.
It really sounds like an exercise in faith.
I'd say it's an exercise in knowledge. Faith is just hoping it works. Knowledge is understanding the system architecture well enough to know why it works.
That makes sense.
That's exactly why a document like the captain's lens exists in the first place, to replace the mystery of the cockpit with mechanics. If you know the logic lock exists, you don't need faith, you just trust the math.
So when do you actually take over? Because you can't just let it roll forever down the runway into the grass. Eventually you have to turn off to go to the gate.
No, you definitely can't let it roll forever. The source pinpoints the exact moment manual control resumes. It's only when the rollout phase is fully complete and the aircraft is slowed down to a safe taxi speed.
So only once the scary high-speed part is completely over.
Right. Once you are at a slow, manageable speed, the auto land automatically disengages. The critical danger has passed. Then, and only then, do you put your hand on the steering wheel for the ground, and you manually taxi the plane off the runway.
The emergency procedure is literally wait until the plane stops.
In this highly specific context, yes. And that is a really hard lesson for pilots to internalize. We are rigorously trained to be Type A problem solvers. The mantra is aviate, navigate, communicate. And aviate usually means grab the stick and fly the plane.
But here, aviate means let the plane fly itself.
Precisely. It's understanding that the best way to pilot in that specific second is to fully surrender to the avionics.
I want to circle back briefly to that idea of redundancy, the Swiss cheese model of failures. Because I can hear listeners thinking right now, okay, but what if the FCU failure was caused by a massive power surge that fried the FMGC brains too?
That's a very valid fear.
Right. Because for the plane to actually crash in this scenario, the document implies that multiple other things would have to fail all at once, right?
Yes. This is the absolute beauty of the architecture. For the plane to actually lose control and crash here, you'd need the FCU panel to fail, and the FMGC computers to fail, and the physical autopilots to fail simultaneously. The odds of that exact chain of events are astronomical. We are talking billions to one.
But the odds of a human panicking at 90 feet?
Much, much higher.
So the weak link really isn't the silicon. It's the biology.
It usually is. The system is deliberately designed to handle the hardware failure. It's the wetware, the human brain, that introduces the unpredictable variable into the cockpit.
That is a very humbling thought.
It is, but I also think it's empowering. Because we can control our reaction. We can study the systems and train ourselves to overcome the startle response.
So let's recap our journey today, because we've covered some pretty dense technical ground from this source. We started in the absolute terror of the fog at 100 feet.
The moment of, oh no, the lights are out.
We learned about alert height, that point of no return, the invisible boundary where the rules just flip.
Where go-round becomes commit to land.
We discovered the logic lock, where the plane effectively stops listening to the manual knobs and completely trusts its own internal brain.
Knobs versus brains, definitely the most critical concept to take away.
And we learned that the plane can actually see with its radio eyes and its inner ears, even when we can't see a thing out the window, allowing it to execute that flare and roll out perfectly.
And finally, the big operational lesson, procedural discipline. Sometimes the absolute hardest thing to do in an emergency is to just sit on your hands.
Trust the logic.
Trust the logic.
Before we wrap up this deep dive, I want to leave everyone with a final thought. We live in an era where we are constantly acting as users. We swipe, we type, we steer, we control everything around us. We expect the machine to wait for our explicit command.
We expect agency. We really define our value by our ability to input commands and solve problems.
Exactly. But as systems get smarter, from self-driving cars to AI diagnostic tools in hospitals, we are shifting roles. In this A320 scenario, the pilot forcefully shifts from being a commander to being a monitor.
And that's a notoriously difficult transition for the human ego.
It really is. So here's the question for you to mull over. As our machines become infinitely more capable of saving themselves in a crisis, is the ultimate skill of the future human simply knowing when not to interfere? Is the highest form of control actually knowing exactly when to let go?
That is the question. And I think for the A320 pilot sitting at 90 feet in the fog, the answer is definitively yes.
Something to think about the next time you're on a flight descending through the clouds. Thanks for joining us on this deep dive. Fly safe.
Take care.